Hello, and welcome to this lecture on a calculus-based physics class, Chapter 9, Linear Momentum. I would like to introduce the concept of momentum to you from a linear calculus-based Physics 1 standpoint, and would also like to discuss the change in momentum, which is namely impulse. I would like to look at some situations, and I will pursue some example calculations in later videos. So let us start by understanding what momentum really is. And how do we define the inertia of motion? Previously, we recall Newton's first law says that inertia is a measure of an object's tendency to stay in the state of motion that it's in. Objects at rest tend to stay at rest, and objects in motions tend to stay in motion in a straight line unless acted upon by a net external force, which we call an outside force. And the way we define that inertia of motion is momentum. Now notice momentum is mass times velocity, and these are vectors. Momentum is a vector, the velocity is a vector. Also notice momentum seems to be a little more fundamental than other quantities studied thus far this semester in calculus-based physics, because notice that it's even more fundamental than mass times acceleration, which is net force. Think of momentum like the measure of sort of the amount of motion of an object. If an object has more mass, it has more tendency to keep moving. If it's already moving in a certain direction, it has more momentum. Notice the units of momentum are not anything fancy. They're just kilograms times meters per second, because that's units of mass and velocity. Note that momentum is not kinetic energy. Kinetic energy is the energy of motion, whereas momentum is sort of the amount of inertia of motion. And kinetic energy we know to be 1/2 mv squared. So notice m times v is momentum, and there's another v and a 2 there. So if you work this through, momentum squared, that's m squared v squared, over 2m is kinetic energy. So you can imagine there's definitely a relationship between kinetic energy and momentum, but in general they are different. So I will perform this simple example in a later video. Okay. So how about force in terms of momentum? The more general form of Newton's second law, that is, the way that Newton himself wrote this law, is expressed as the time rate of change of momentum. Remember that Newton's second law tells us about net forces, but the way Newton himself wrote down net force, or the sum of all the vector forces, is the change of the inertia of an object vector, that's the momentum, with respect to time. Now notice momentum, we recall from the previous slide, has two parts, mass and velocity, velocity being a vector. So if we want to examine each of those changes separately, we should use the product rule for derivatives. That is, we should take the time derivative of mv vector. Notice we get m dv vector dt plus v vector dm dt. Now notice, m dv vector dt, you should recall what that is from earlier in the semester. That's mass times acceleration. Whenever an object has a constant mass, its velocity changes with time. That would also change the object's momentum, and then as a result, we have mass times change in velocity with respect to time. So that's certainly one way to get a net force. But notice this second term. This is something we have not discussed so far yet this semester. If velocity is constant, but the mass is changing in time, then you have v vector times dm dt. Okay? So notice you could try to think of a couple examples of what that would actually look like. Imagine that if a freight car is moved along and a bunch of coal is dumped into it. You could imagine the mass goes up in time. Even if the velocity stays put, there's a large force on the object. You could also imagine that when, let's say, a rocket is taking off, it's burning a lot of fuel. its mass is, say, decreasing in time. And since its mass is decreasing in time, if there's no net force, if it's moving at, let's say, a constant velocity, then its velocity should go up as its mass gets less. So those are kind of things that you should think about. So notice this equation again reduces to F vector, sum of all the forces, equals ma vector when the object's mass does not change. And notice that a net force is more generally constant mass with a velocity change in time, which we call an acceleration, or constant velocity with a mass changing in time. Okay? Again, I will look at another example of this in the videos to come. I also want to discuss the concept of impulse. Now, what is the term impulse? I think impulse is a lot less of a common physics term that's thrown around in the real world. An impulse is going to be the change in momentum. Think of impulse as sort of the oomph of a collision or interaction. Usually that's when time is quite small. Now, impulse is going to be the symbol capital I, which I will denote as a cursive capital I in this class because regular capital I is reserved for something else. And then that's going to be the change in mv, because it's the change in momentum. And interestingly enough, that would be force times a time interval for a constant force. So one thing we've talked about this semester is forces, but we haven't talked about the time period that they're imparted over. So that would be the impulse. Now let's think about a couple situations where if we think in terms of impulse, we will help ourselves understand this concept. Imagine that a force is constant, but imagine that something else changes the impulse. Imagine we're going to hit a golf ball with a club, and we want to ask the following question. Why do we follow through in a golf swing? So if you swing a golf club, you don't stop your swing, otherwise the ball won't go very far and it's not a very effective golf swing. You swing all the way through and follow through with the golf club. And the idea is that if you stopped your swing, sure, the ball would be in contact with the club, but for a short amount of time. If you followed all the way through the ball would be in contact with the club longer. The ball would sort of deform and stay in contact with the club longer, so you would increase the time of collision. But if you have the same force in both swings and increase the time in collision, you get a greater impulse, thus you get a greater change in the object's motion. So following through in sports, I mean the same thing would be true if you swung through a tennis ball if you were playing tennis. When you follow through hitting something in a sport, you get a greater impulse, that's a greater momentum change, and then a greater motion to the object of interest. What if you have two situations with the same momentum? Let's suppose a boxer is being hit by a punch. Hopefully his trainer, maybe his trainer is like Mickey, who was training Rocky, told him to roll with the punches. And you even hear about this in motivational settings. What does it mean to roll with the punches? Well, it's the opposite of standing still to take a punch. If you roll with the punches, if a punch comes in and you allow the time of contact to be very long, that you move your face along with the punch, the force won't be quite so large because the time is extended. The same mass of the hand with the same velocity comes in, thus it has the same momentum, and it's also going to have the same impulse. Whereas, if the person stands there and takes the punch very suddenly, there's going to be a much shorter time of interaction, so the force will be greater. Thus you have a much larger impulse, you have the same impulse, but you have a much larger force because the time is reduced. Notice, the same punch can be absorbed two ways. So it's much better to roll with the punches, increase the time of the interaction to not have such a large force resulting. And let's think of one last scenario. Suppose objects have the same mass and velocity, and suppose we have two balls, both of the same mass. One is a rubber ball, one is a putty ball. One is going to bounce off of a wall, and the other is going to stick to the wall. Which is going to have the greater impulse in the collision? Well, the object that bounces off the wall is going to have positive momentum going in, momentum's a vector, and it's going to have negative momentum going out. Whereas the ball that sticks to the wall is going to have positive momentum going in and then zero momentum. So as a result, the object that has a greater directional change, because velocity is a vector, is going to have the greatest change in momentum. So an object that bounces has a greater impulse than an object that sticks. Now, by the way, if you've ever watched sports, especially, say, football players colliding, when they collide and they bounce, that's a very violent collision. But when they hit and they stick, they destroy a bunch of their energy, which goes into heat. I'll say more about this when we study collisions in detail, but that one is not going to be nearly as violent of a collision because there's not that directional momentum change. So remember, change of momentum is impulse. Make sure you understand this concept. Now, I've only really discussed the intuition and the concept of impulse. I haven't discussed its equation, its derivation, and I haven't made much of it as a vector. Separate the generalized version of Newton's second law as a differential equation. So dp vector dt equals to net force. If we move the dt over, if you integrate each side of this equation from some initial to final state, you should have the following situation. The integration of mv is the integration of f dt. Notice that here we're integrating just the quantity of momentum. Here we're integrating the f vector dt from some initial to final time. So the change of momentum is the impulse, and that's going to be the time integral of f vector dt from t initial to t final. Notice that we would use this situation, namely that we should take the integral of f vector dt from some initial to final time to find the impulse, if the force is not constant. So if we don't assume some average or constant force, or if the force is variable over time. So if force is a function of time, we can use this. Now remember, like I've said several times in this course, I would either need to give you force as a function of time, or I would need to give you a graph of f versus t in order for you to figure out this integral. Okay? So notice that if I do give you a graph, force versus time, there exists a time-dependent force. The impulse can be deduced. So geometrically, we know this, if f is plotted versus t, that the impulse is the area under the curve. The impulse is the change in the momentum. By the way, notice I'm calling this the area under the curve, but I might be better said to call it the area between the curve and the horizontal axis. Because if impulse is negative, then this curve would be below the t-axis, and that would be a negative impulse. Notice a negative impulse would be like a negative change in momentum, but a negative change in momentum could be just due to the direction. So, in fact, let's actually look at a negative impulse. That is from a ball that's moving to the right, that's going to hit against a wall, that's going to be in contact with a wall for a period of time, deform for a short period of time, then bounce off. So notice that if you imagine a rubber ball bouncing off the wall, the ball initially travels towards the right, so the initial velocity and the initial momentum, linear momentum, are positive. Okay? Notice the momentum begins at its maximum positive value. Once the ball starts to come in contact with the wall, notice that there then starts a negative impulse. That's because the force is to the left, in the negative x direction, and the fx is negative, and thus the impulse is negative. Now notice what that's going to do is during the contact, it's going to slow down the positive momentum to cause the ball to stop and then cause it to attain negative momentum until the ball bounces off of the wall. The impulse then goes to zero because it's no longer in contact with the wall, and now the ball has negative momentum. Notice that the change from the initial to the final momentum is capital J, capital I, which is the impulse. And then notice that it's in the x direction, it's exactly horizontal. And this area under the force versus time curve is exactly the impulse. Notice this impulse is the area under this curve, but it's not a constant because the force is changing in time. The force is actually greatest when the ball is most deformed and the ball is stopped, but the force gets less as there's less contact with the wall. Now, in many cases, it's very difficult to assess this force versus time curve, so we often estimate that area and assume that the force is constant and take some sort of an average force, and then the impulse vector is the sum of all the average force vectors times delta t. In other words, we assume the force is constant and we don't have to per se take an integral. So I will perform this example in an upcoming video to show how impulse works. Now, suppose we go back to that rubber ball for a second. Sometimes this is often assessed with before and after bar graphs. The ball was initially moving to the right. It had positive 2 kilogram meters per second of linear positive momentum. It encounters over the course of time, let's say negative 4 newtons times seconds, now that would be the same thing as kilogram meters per second, of impulse, which is to the left. So the final momentum is negative 2 kilogram meters per second to the left. That's because the ball rebounds with no loss of speed. Now, I want to do one more thing in this lecture, and that is compare impulse and the change of momentum to the work kinetic energy theorem. Because you may ask, well, wait a minute, force versus another variable looks similar to what we studied in the energy chapters. So here's the impulse-momentum theorem. The change in momentum is equal to the impulse vector, and that's the integral from t initial to t final of the sum of the force vectors times dt. So that's the integral of the net force dt. Notice that the impulse is the area between this force versus time graph and the horizontal axis. How about the work kinetic energy theorem, though? Remember that that's the change in kinetic energy is the work, and that's the integral from x initial to x final of the net force, dx. So notice that if force is plotted versus some displacement, the work is the area under the force versus position graph. Notice impulse and work are both area between a variable force and a horizontal axis. That's what's the same. But what is different is that impulse is how a force unfolds over a time to create a momentum change, whereas work is how a force is exerted over a displacement to transfer energy. Impulse depends upon the time interval that the force acts. Work depends upon the spatial or the displacement interval over which the force acts. Notice they're somewhat similar, but they are definitely different, and they arise different quantities. So I hope that makes sense. Thank you very much for your attention. This ends the following lecture on the introduction to momentum and impulse. Please smash that like button and give it a thumbs up if you enjoyed. Please subscribe to this channel, and I will see you in the next video.